Hello friends, I welcome you in this particular session where we are going to discuss one of your core subject for electrical engineering for upcoming GATE 2026 examination. So hello friends, a very warm welcome to all of you. Just quickly confirm in the comment section whether my audio, visual, everything is clear so that we can start with the session. So today is going to be the second part of this particular subject. Already we have covered the first part yesterday and we have covered somewhere up to the transmission line part, and that is the point from where we are going to start today. So everybody who is joining me live, just quickly confirm your presence and tell me audio, visual, everything is clear so that we can start with the session. Now till you are going to tell me about the audio and visual quality, let me just brief you that what we were discussing in the last class. If you see, I think in the last class we were talking about the transmission line, and in that we were discussing the types of transmission line conductors. Types of transmission line conductors. We have discussed about different types of transmission line conductors. So we have discussed the single solid conductor. We have discussed the stranded conductors. We have discussed the bundled conductors. And the last topic that we were discussing in the yesterday's session was how to calculate the geometrical mean distance and geometrical mean radius. Everybody who is joining me live, just quickly tell me in the comment section, are you able to follow? Yes, everyone. And please quickly share the session with your friends and colleagues so that everybody can join the session. Okay, so let us start from this point only. But before we start, let me just brief you about my introduction. Let me just give a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have around 15 plus years of teaching experience. I have completed my MTech from IIT BHU in 2010 and I have written a couple of books. Basically, I am an electrical engineer and deal with most of the core subjects of electrical engineering, and apart from this, I also teach some non-technical subjects, especially engineering ethics. Okay, so you can join my personal Telegram channel on GFG platform, and you can also join the Geeks for Geeks GATE Telegram channel so that you remain updated for any important notifications as far as your GATE examination and various other PSU's examinations are concerned. You must be knowing that recently the Geeks for Geeks platform has started with the electrical and electronics courses, and that we have already launched. The classes are going to start from 23rd of February. Apart from this, we have started number of initiatives which are free of cost for all those candidates who are seriously preparing for GATE 2026 examination. Currently, we are having the Maha Revision part. After this, we will be coming up with PYQ series also, and then we will be also coming up with the formula series, and so many things we are going to have for you guys only. Okay. So already we have launched the GATE 2027 and GATE 2028 matches for electronics and electrical. If you want to see those courses, you can go to the GFG platform and you can just read about these courses, and if you are interested, then you can join. So let me just start with what we have left. So we were talking about the calculation of GMD and GMR. Now let me give you some examples that how you are going to calculate the geometric mean distance and geometric mean radius. Okay. So let me just give you case 1. Suppose you have a single conductor. Single conductor means it's only one conductor. It is only one conductor, and suppose its radius is going to be R. Now, if it is only one conductor, you know that you cannot find the geometrical mean distance, because geometrical mean distance we can only find in between two different groups or the phases of conductors. If it is only one conductor, then you cannot find the geometric mean distance because it is the effective distance between two different groups of conductors. So GMD is not possible and not meaningful. So we are calculating GMR, that is geometrical mean radius. Geometrical mean radius or geometric mean radius is nothing but the effective radius of the conductor. So we have to introduce a factor that is 0.7788 multiplied by the radius or the physical radius of the conductor. Why this factor is coming, that we will discuss when we will talk about the line constant calculations. Okay, we'll talk about the line constant calculation and then we are going to discuss it. Okay. Suppose you have another case where it is a single phase two wire system. If it is a single phase two wire system, something like this. So one conductor is going to be the forward conductor and the other conductor is going to be the return conductor. This is the forward conductor, suppose, and this is the return conductor. This is the return conductor. Okay. So if the distance between them is somewhere, suppose D, okay, so directly you can write the geometric mean distance. Directly you can write the geometric mean distance, because what is geometric mean distance? It is the effective distance between the two groups or phases of the conductor. So you have two groups of conductor and in each group you have only one conductor. So if I ask you what is the effective distance between them, it is simply D. It means GMD you can easily write. So GMD is nothing but D. Sir, you have to calculate GMR for these conductors? Yes. If you have to calculate GMR, you have to calculate GMR separately for A and separately for B. And the procedure is same. So if I am writing the GMR, for A conductor, suppose, okay, for A conductor, or let me write it in capital, A conductor. So it is simply 0.7788 multiplied by its radius. If I am writing the GMR for B, it is simply going to be 0.7788 multiplied by its radius B. Everybody just tell me in the comment section, are you able to follow this or not? I am not able to see your comments. And please share the session with your friends and colleagues. I think some of the students who were present in the yesterday's class, maybe they are not aware. Maybe they are not aware, so they will lose. They will lose. Let us take another case. Okay. Let us take another case. Suppose I am taking the case of a three-phase system. And we are talking about the general case. So let us take the unsymmetrical spacing. Unsymmetrical spacing means what? Unsymmetrical spacing means, suppose you have three conductors for three different phases in such a way so that their spacing is going to be different. Their spacing is going to be different. Something like this. Suppose you have three conductors representing three different phases of your system, of your three-phase system. So suppose this is going to be the A phase, this is the B phase, and this is the C phase. Suppose the distance between them is going to be, suppose this is A, this is C, and this is B. So if I ask you for this three-phase system, what is the GMD of this system? What is the GMD of this three-phase system? So how I am calculating, just see it very carefully because it is going to be very important. If you understand it in one go, whatever problem you are going to face in the calculation of GMD and GMR, you are never ever going to do any mistake. Okay. Suppose you are calculating the GMD of this system. Why I am saying GMD of this system? Let me just tell you one reason. I will tell you when we will talk about the line constant calculations that for three-phase systems, if you have the GMD system, then directly you can write the inductance as 0.2 ln GMD system upon GMR system. Okay, that is millihenry per kilometer. Okay. So that is the reason we are talking about GMD system. Sir, how I am calculating the GMD system? Please see this. For this unsymmetrical spacing three-phase system, if I am calculating the GMD system, what I am doing, I am finding GMD for A, I am finding GMD for B, and I am finding GMD for C, and then I am finding the geometric mean of these three GMDs. So what I am doing, I am writing GMD A, GMD B, and GMD C. It may look like that it is a long or lengthy method, but I will tell you the shortcut. What is the shortcut? Now, if you calculate GMD A, how you are going to do it? If you are calculating GMD A, it means what you have to do? For finding GMD A, you have to find the distance between A and B and A and C phases and take its geometric mean. This is how we define the geometric mean distance. So it is going to be what? It is going to be distance of A to B and distance of C to A. And what is the effective root? 1 by 2, because there are two distances. GMD is nothing but a distance. So it is 1 by 2. Similarly, you can find the GMD for B conductor. GMD for B conductor is going to be the distance between B and C and the distance between A and B power 1 by 2. Similarly, you can find the GMD for C conductor, which is going to be the distance between B and C and the distance between C and A, and power is 1 by 2. Now, keeping these values, you can find the GMD system. So, what is going to be GMD system, dear? So, GMD system is, now you see this, DAB, DCA, power 1 by 2, Then GMDB, that is DBA, DBC, power 1 by 2. And then GMDC, that is DCA or DBC, power 1 by 2. So there are 1, 2 and 3. So power is 1 by 3. This is how we were calculating the GMD system. Yes or no? Now if you simplify this now, what you are getting as GMD system is nothing but the distance between A and B, the distance between B and C, and the distance between C and A, and take 1 by 3 or cube root. It means this is the shortcut for writing the GMD system for a three-phase system. If you know the distance between A and B phase, B and C phase, and C and A phase, irrespective of their spacing. Even if it is going to be, suppose it is vertical spacing. Vertical spacing is going to be something like this. So generally we are using the vertical spacing when we talk about the transmission line. When we talk about the transmission line, then we talk about vertical spacing. Okay. So this is A phase, this is B phase, this is C phase. The distance between A and B is DAB. The distance between B and C is DBC. And the distance between A and C is going to be DCA. So irrespective of the spacing between the A, B and C conductors, you can directly find the geometric mean distance in case of a three-phase system. What you have to do? You have to write GMD system is nothing but distance between A and B, B and C, C and A, and take the cube root 1 by 3 because there are three distances and you want one distance. GMD is nothing but a distance. All of you, can you tell me yes or no in the comment section? Yes? Hello, hi, good evening everyone. At least tell me yes or no, are you able to follow me or not? Okay. So vertical spacing where we are using, generally we are using the vertical spacing for transmission lines. For transmission line. We can also talk about the horizontal spacing. Horizontal spacing we are using for the distribution system. Horizontal spacing. Generally we are using for the distribution system and it is something like this. It is something like this. It is something like this. So this is going to be A phase, B phase and C phase, and again the interphase distance is going to be DAB, DBC and this is DCA. So again if you have to find the GMD system, you can write it, that is DAB, DBC and DCA. What is the effective root? 1 by 3 because there are three distances. Everybody just tell me yes or no in the comment section. Are you able to follow this? So irrespective of the spacing, because we have discussed the general case for the unsymmetrical spacing, so directly multiplying the interface distances and taking the cube root, you will get the GMD system. No problem with the GMD system. How you are going to calculate the GMR? The same way. You have to calculate the GMR for A, GMR for B, GMR for C. Are you getting that? So there are two ways in which you can do it. Either you calculate the GMD and GMR for A phase separately. You find the A phase inductance separately. You write the GMD and GMR for B phase and find it separately. You find the GMD and GMR for C phase and calculate the inductance separately. And then you can calculate the average so that you can calculate the per phase inductance of a given three-phase system. The other way is you find the GMD system, GMR system and directly write the inductance. It is approximately going to be the same thing. Approximately it is going to be the same value, okay, almost same. So we have discussed about the GMD when we are calculating GMD for three-phase system. Let us discuss some more cases. Suppose I am talking about the stranded conductors. When we talk about the stranded conductors, one of the most interesting case is bundled conductors. How you are writing it, just see this. For bundled conductors, if the conductors are like this, okay, something like this. This is conductor number 1, this is conductor number 2. And they both belong to A phase. They both belong to A phase. Are you getting this? Because A phase conductor we have divided into two subconductors. That is what we call as bundled conductors. Similarly, you can write for the B conductor or the return conductor as a composite of two small conductors or subconductors. So this is going to be B. Again, this is 1 and this is 2. Now for this system, suppose the effective distance is given as D. So GMD is not a problem here because directly they are giving you the effective distance D. So GMD will be the effective distance between these two group of conductors A and B. But if you have to calculate GMR, how you are calculating the GMR? Just see this. Suppose I am calculating GMR for A. So GMR for A is going to be GMR for A1 multiplied by GMR for A2. What is the effective root? 1 by 2. Now, if you see, because of the very nature of symmetry of these two subconductors, whether you calculate GMR for A1 or GMR for A2, it is going to be the same thing. Because of symmetry, you can say GMR for A1 is going to be same as GMR for A2. GMR for A2. And this is the reason. GMR A, you can directly write as GMR A1 or as GMR A2. So if you write for 1 or 2, it is going to be the same thing. So how you are going to write it? Suppose I am writing for A1. So it is going to be 0.7788 multiplied by its radius. Suppose its radius is R. Okay. Multiplied by the distance between 1 and 2. So the distance between 1 and 2, suppose we are saying as small s. So small s is also going to come here. And you have to take the effective root. This is one distance, this is another distance, two distances. You need one distance. What is the required root? It is 1 by 2. Are you getting this? This step everybody is getting, how to write GMR for bundled conductors. Similarly, you can write the GMR for B conductor also. Are you getting that? I hope it is clear. The next case we can discuss, and we can talk about the GMR in case of bundled conductors. Sorry, stranded conductors. Stranded conductor. So if it is a two-layer stranded conductor, can you tell me in the comment section how many conductors are going to be there? Yesterday I told you the pattern. If you remember that the first layer is going to be the core conductor. This is the first layer. Okay. This is the first layer. And these 6 strands are going to comprise the second layer. Okay. So if you have this type of stranded conductor, how you are calculating the GMR? See, very, very important. Suppose I am going to name these conductors. Okay, 1, 2, 3, 4. So how I am writing? Suppose this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So total 7 conductors we have. So what I am going to do, I am going to find the GMR for all these 7 strands and then take the geometric mean. So I can write GMR1, GMR2, GMR3 up to GMR7. How many GMR I am having? 7. How many GMR I need? 1. So what is the effective root? 1 by 7. What is the effective root? 1 by 7. Are you getting this? I hope you are getting this. Now if you see, because of the nature of symmetry, the strand 1 is going to be different in comparison to all other strands. But if you see strand number 2, 3, 4, 5, 6 or 7, they are in a symmetrical nature. They are symmetrical, yes or no? If you see 2, you have 3, 1, 7, 6, 5, 4. So similarly, if you talk about 4, it has the same nature of strands around it. It means if you calculate GMR for 2, 3, 4, 5, 6, 7, it is going to be exactly same because of the nature of symmetry. So because of the nature of symmetry, the GMR 2 is going to be same as GMR 3 is equal to GMR 7. So 2 to 7 GMR is going to be exactly same. Only GMR 1 we have to calculate separately. So what I am going to do, just see this. I can write GMR 1 GMR 1 I have to calculate separately, and GMR 2, 3, 4, 5, 6, 7, they are going to be exactly same. So GMR 1, how I am calculating? I am writing for GMR 1. So GMR 1 is going to be 0.7788 multiplied by the radius of strand number 1, that is R, and the distance between strand number 1 with all other strand within the same phase, within the same group. So it is going to be distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and 1 and 7. So I am writing D12, D13, D14, D15, D16, and D17. How many distances? How many distances? 1, 2, 3, 4, 5, 6, 7. What is the effective root? 1 by 7. GMR 1 we have calculated. You calculate any of the GMR 2 to 7, it is going to be same. What is going to be GMR 2? Effective radius of strand 2, that is 0.7788 into R, and the distance between 2 to 1, 2 to 3, 2 to 4, 2 to 5, 2 to 6, and 2 to 7. How many distances? 1, 2, 3, 4, 5, 6, 7. So effective root is 1 by 7. Effective root is 1 by 7. Everybody just tell me in the comment section, are you getting this? Last year, maybe I think 24 or 23, they have asked one question on calculating the GMR for a standard conductor, but there was a small trick. What was that trick? I will tell you. When we talk about the standard conductor, you may have composite stranded conductor. Composite stranded conductor. Suppose I talk about a hypothetical stranded conductor. Hypothetical stranded conductor means, just for the sake of understanding, we are discussing it. It is not possible. Because for proper stranded conductor, we need a core strand, then 6 strands around it, forming the second layer, and then 12, then 18, then 24, then 30, and then 60. So if you are having the composite stranded conductor and we are talking about hypothetical conductor, suppose the conductor is something like this. Suppose the conductor is something like this. So if you have seen the previous year paper, you must be remembering this particular question. Something like this. The only trap or the trick was, that this was a steel conductor. This was a steel conductor. This was a steel conductor. This was actually a steel conductor. Rest were aluminum conductors. Suppose this is the case. So this is a steel conductor and rest are aluminum. Rest are aluminum. Okay. I think it is visible. Now when you calculate the GMR for this particular conductor, how you are calculating? See, suppose this is conductor number 1, this is conductor number 2, this is conductor number 3, and this is conductor number 4. Whenever steel strands are going to be there, while computing the GMR, we will not account for those strands which are steel, which are made of steel. Because steel strands are not going to carry the current. Even though they are going to be accountable in terms of the spacing. If you find the space between 1 and 3, then it is going to be accountable. But while calculating the GMR for this standard conductor, we will not introduce or include this conductor number 4 because it is made of steel and it is not going to carry any current. So, sir, how I am writing GMR? It is nothing but GMR1, GMR2 and GMR3. How many GMR3? How many you want? 1. Take the effective root 1 by 3. If you remember this question was previous year GATE question, maybe 23 or 24. GATE 23 or 24. Rest you can do easily, there is no problem. Okay. So you understand how to do for standard conductors also. Okay. So let me just discuss one or two questions regarding this so that you understand it better. One or two questions let us discuss. Just see this particular question. I hope this question is visible. So this is basically a single phase line. You can see there are two groups of conductors. Forward conductor, this is the forward conductor, and this is the return conductor. This is the return conductor. The forward conductor is having 3 subconductors A1, A2, A3. And the return conductor is having 2 subconductors B1, B2. And he is asking to find the inductance of this single phase line. How you are calculating it? Just see this. If I am writing the inductance of this line, because one is forward, one is return. So L total or the total inductance, or we call it loop inductance, it is going to be inductance of A and inductance of B. It means I have to calculate the inductance of the forward conductor, suppose it is A, and the inductance of B conductor, and then add them up. This is the procedure. So suppose first I am writing the GMD for A conductor. I am writing GMD for A group of conductors. How I am writing? Just see this. How I am writing GMD for A group of conductors. So I will be writing for GMD for A1, GMD for A2, GMD for A3, and then I will take the geometric mean. So it is GMD A1, GMD A2, GMD A3. What is the effective root? 1 by 3. Now you see how you are writing GMD A1. Just see this. GMD A1 is the distance between A1 B1 and A1 B2. So distance between A1 B1 and distance between A1 B2. And what is the effective root? 1 by 2. Because two distances, you need one distance, take the effective root. That is 1 by 2. This is how you calculate GMD A1. What is GMD A2? Again, distance between A2 and B1, A2 and B2. A2 and B1 and A2 and B2. Two distances, what is the root? 1 by 2. Then I am writing GMD for A3. It is the distance between A3 and B1, A3 and B2. A3, B1 and the distance between A3 and B2. How many distances? 2. What is the effective root? 1 by 2. How simple it is going to be if you go step by step. How simple it is going to be. The moment you calculate GMD for A1, A2, A3, put them here and you will get the GMD for A. I am not doing the exact calculations, that will take time. So you can just do it as a homework. I am telling you the procedure. Similarly, if I have to calculate the GMD for B conductor, how I am going to do? Just tell me. Now you can tell me. If I am writing GMD for B, so it has B1, B2, so I will write GMD for B1 and GMD for B2. Power is 1 by 2. What is GMD B1? The distance between B1 and all other conductors all the conductors in the other phase or group. So it is A1, A2, A3. So distance between B1A1, B1A2, B1A3. So distance between B1A1, B1A2 and B1A3. How many distances? 3. What is the power? 1 by 3. If I am writing GMD for B2, so I have to write distances between B2 and all the conductors in the other phase or group. So B2A1, B2A2, B2A3. So it is distance between B2A1, B2A2 and B2A3. What is the power? 1 by 3. Now you can easily calculate GMDB. We have calculated GMD for A and B separately. Let us calculate GMR for A and B. Let us calculate GMR for A and B. If I am writing GMR for A is having 3 subconductors. So I will be writing GMR A1, GMR A2, GMR A3. How many GMR? 3. How many GMR you want? 1. So what is the effective root? 1 by 3. Similarly, I can write GMR B as GMR B1 because there are 2 subconductors. GMR B2. How many GMR? 2. How many you want? 1. What is the effective root? 1 by 2. Now you can easily calculate GMR A1, A2, A3, GMR B1, B2 separately. How I am calculating GMR A1? Just see this. GMR A1. Always remember, whenever you calculate GMR, GMR is only calculated within the same phase or group of conductors. It means when I am calculating the GMR for A1, I am only interested in the conductors or the subconductors in group A or phase A. Are you getting this? So GMR A1 if I am writing, first I will write the effective radius of A1, that is 0.7788 multiplied by R. Okay. Let us see the radius. So radius is R1 and R2. For A group it is R1. For B group it is R2. So we'll go for R1. So for A1 it is 0.7788 into R1. And the distance between A1 with all the conductors within the same phase or group. So it is A2, A3. So the distance between A1 to A2 and A1 to A3. Yes or no? The distance between A1, A2 and distance between A1 and A3. How many distances are there? 1, 2 and 3. What is the effective root? 1 by 3. Similarly, you can write GMR for A2. Effective radius of A2 0.7788 multiplied by R1. Distance between A2, A1 and A2, A3. Power 1 by 3. If you have any doubt while I am writing this, you can ask me, because this is the time you can remove all your confusions for any problem you see in calculation of GMD and GMR. Otherwise, throughout you will be having this or that confusion. If you have any doubt, you can clear it right now. We are also going to discuss about the double circuit line also. I am not going to leave any case unanswered. And this year, I expect that you will get a question in GATE. I am writing this because after the GATE examination, GATE 2026, at least one question you will get from the calculation of GMD and GMR. At least one calculation. At least one question you will be getting from calculation of GMD and GMR. It may be bundled conductor, it may be stranded conductor, it may be a double circuit line. Okay. How I am writing for GMR A3? Now when I write GMR for A3, I will write the effective radius of A3 and I will multiply it with the distance between A3 and A2 and A3 and A1. Because there are 3 subconductors in group A or phase A, you can say. So while writing GMR for A3, I have to simply write the effective radius of A3, that is 0.7788 multiplied by R1. and the distance between A3, A1 and distance between A3, A2. How many distances? 3. What is the effective root? 1 by 3. I'm not getting your comments. I don't know whether you are able to follow me or not. I'm shouting like anything. Similarly, if I'm writing GMR for B1, we have two subconductors in B group, that is B1 and B2. So B1, write the effective radius of B1 0.7788 into R2 for B group of conductors. Subconductors, the radius is R2. So effective radius is 0.7788 into R2 and the distance between B1 and B2, only two subconductors. How many distances? 2. What is the power? 1 by 2. How I am writing GMR for B2? It is 0.7788 R2, that is the effective radius of B2, and the distance between B2 and B1. What is the effective root? 1 by 2. So you can now calculate easily GMD and GMR separately for A and B group of conductors. If you can calculate this, can you calculate the inductance of A? Yes, it is 0.2 ln GMD A upon GMR A millihenry per kilometer. What is LB? 0.2 ln GMD A upon, GMD B. We are talking about written conductor. And this is GMR B. This is millihenry, this is per kilometer. This is millihenry per kilometer. Everybody just tell me yes or no. Yes. The moment you get A and B, now you calculate the total or the loop inductance. That is nothing but LA plus LB. That is nothing but LA plus LB. Yes, Nishant Yadav, how are you? Yes, Gumnav. Very interesting name. I'm not able to pronounce. So this question we have done. Let us do one more question. Okay. Now there is a double circuit line. So before we proceed for this, let us talk about the double circuit line. Let us first talk about the double circuit line. What is double circuit line? Double circuit line, little interesting. Double circuit line. As the name indicates, double circuit, it means for one individual phase you are using two parallel circuits. Initially what we were doing, we were using bundled conductors. Instead of one conductor, we were having more than one conductors and giving some spacing to them. But this time what we are doing, we are having a completely separate circuit, two parallel circuits going for one phase. So it's going to look something like this. It's going to look something like this. Just see this. So this is a transmission tower having a double circuit line. Just see this. Suppose the conductors are going to be something like this. Now understand very carefully, extremely important, understand very carefully what is double circuit line, okay? Most of the people, they are having this confusion. When I am writing A1 and A2, see very carefully, A1, A2. These A1, A2 are bundled conductors. These are subconductors. Distance between them is S. So A1, A2, or if I write B1, B2, or if I write C1, C2, This A1, A2 bundled conductor, B1, B2 bundled conductor for B, C1, C2 bundled conductor for C. But double circuit line does not stop here. For A phase, it is not just one circuit, you have a parallel circuit. Suppose this is going to be A1 dash and A2 dash. It means this A1, A2 part of one conductor, it is one bundled conductor. Another circuit for A phase is having A1 dash and A2 dash as the bundled conductor. I hope you are getting this. I hope you are getting this, the difference between bundled conductors and double circuit line. Bundled conductors, you are simply dividing one conductor into different subconductors. But that is just one group of conductor for A phase. Here what we are doing, for A phase we have two separate parallel lines, that is why we call it double circuit line. I hope you are getting this. I hope you are getting this. So A1, A2 and A1 dash, A2 dash, they belong to one phase, that is A phase. This is suppose B1 dash, B2 dash, and this is suppose C1 dash, C2 dash. Now the problem here is not the calculation of GMR, but the calculation of GMD. GMR you can calculate, na? Hello? GMR you know how to calculate. GMR you can calculate. The problem is finding the GMD. Suppose it is not A1, A2. This is simply A1. And this is not A1 dash, A2 dash. It is simply A2. So can you calculate the GMR? Yes. Yes or no? Already we have calculated. Very simple. How to find the GMD? Finding GMD is very difficult here. Why? The distance between the A1, A2 and A1 dash, A2 dash has become almost similar to the distance between phase A and B, B and C, or C and A. It means within the same phase we have two circuits which are placed almost at approximately at the same distance as if your phases are placed. So how to calculate the GMD? It is very difficult. So for a double circuit line, how to calculate GMD system? Find DAB equivalent, DBC equivalent, DCA equivalent, okay, and how many distances you are getting? 3, so the effective root is 1 by 3. Now here what is what is DAB equivalent? This is very interesting. Suppose you have this case. Suppose you have a double circuit line like this. I am just drawing one. Double circuit line like this. Double circuit line like this. Okay. Now you will better understand a double circuit line. So you are having two parallel circuits. Suppose this is A1, okay, A1, B1, C1. Suppose this is A2, B2 and C2. Okay. So A1, A2 belong to the same phase but having two different circuits. So what is the meaning of this DAB equivalent? Let us try to understand how I am writing DAB. DAB equivalent says the distance between A1, B1, A1, B2, A2, B1, A2, B2. How many distances? 4. What is the effective root? 4. What is DBC equivalent? You have to find the distance between D, B1, C1 dB1C2, dB2C1, dB2C2. How many distances? 4. What is the power? 1 by 4. Similarly, you can write dCA equivalent. Distance between C1A1, C1A2, distance between C2A1, C2A2. How many distances? 4. What is the power? 1 by 4. So you have calculated the equivalent DAB, DAB equivalent, DBC equivalent, DCA equivalent. Just use that formula and you can find the GMD. Everybody just tell me in the comment section, are you able to follow this? I think today there was a change in the time. Maybe because of this reason people are not able to join. So if you are connected to anyone, I think you can help them just by sharing the link if you are connected. Everybody just tell me, are you getting this or not? How to write the GMD for double circuit line? Are you getting this? So let me show you this question. You may get this type of question in your examination also. You see, it is a double circuit line. He is asking find the inductance per phase of the following double circuit line. A1, B1, C1, C2, A2, B2. Now here A1, A2 belong to the same phase. B1, B2 belong to the B phase and C1, C2 belong to the C phase. How you are calculating GMD system? Just see this. It is DAB equivalent, DBC equivalent, DCA equivalent. What is the effective root? 1 by 3. How you are calculating DAB equivalent? Just see this. DAB equivalent. How you are writing? Again remember, distance between, see, now I am doing it directly. I have already written the formula. Now I am doing it directly. You can correlate. I am writing DAB equivalent. So I am writing the distance between A1, B1, A1, B2, A2, B1, A2, B2. Are you getting this? So distance between A1, B1 is 3. Distance between A1, B1 is 3. Distance between A1, B2 is 1, 2, 3, 4, 5. 5 नहीं 15. 15. Yes or no? Distance between A1, B1 हो गया, A1, B2 हो गया. अब A2, B1, it is 3, 3, 6, 3, 9. So it is 9. Distance between A2 and B2, 3 meter. How many distances? 4. What is the power? 1 by 4. See how easy it is. BC equivalent, DBC equivalent. The distance between B1, C1, 3. B1, C2, 6. B2, C1, 9. And B2, C2, 6. 3 plus 3, 6. Power 1 by 4. Sir, what is DCA equivalent? Distance between C1, A1, 3 plus 3, 6. C1, A2, again 6. You also do this parallelly. Now this is C2, A1. This is C2 and this is A1. C2, A1, 9. And C2, A2 is 3. So this is 3. How many distances? 4. So power is 1 by 4. Everybody tell me in the comment section. Beyond this, they are not going to ask even in the GATE examination. And if you understand this, how to calculate GMD, GMR for these cases, I think no examination, not even in India, even beyond India also, is not going to trouble you. Okay, that is how we are discussing it. If you calculate GMR also, so you have to calculate GMR for A, GMR for B and GMR for C. How many GMR? 3. You want 1, take effective root. How you are calculating GMR A? I am just showing you. GMR A is going to be GMR A1 into GMR A2. Now again you see the symmetry. Why I am saying symmetry? Just see this. If you stand at A1 and see towards A2, what is the distance? 3, 3, 6, 3, 9, 12. If you stand at A2 and see the distance with respect to A1, again it is 12. It means as far as A1, A2 are concerned, they are symmetrical with respect to each other. So if they are symmetrical with respect to each other, it means whether you calculate GMR A1, because what is GMR A1? Effective radius of A1 and the distance between A1 and A2. Similarly, if you write for A2, GMR A2, so the effective radius of A2 and the distance between A2 and A1, so definitely because the nature of the symmetry, these two GMRs are going to be same. So directly you can write, because of the symmetry, because there are only two conductors, two circuits, GMR A1 is same as GMR A2. So you can simply write GMR A. If you write it as GMR A1, suppose, you can write it as A2 also. So effective radius of A1, that is 0.7788 into R, and the distance between A1 and A2, and that is 12. How many distances? 1 and 2. What is the power? 1 by 2. Similarly, you can calculate GMR for B. Again, directly you can write GMR B1 is going to be same as GMR B2, and that is equal to GMR for B because of the nature of the symmetry. So the effective radius of B1, so it is 0.7788 into R, and the distance between B1 and B2. So distance between B1 and B2 is going to be again 12. Power 1 by 2. Similarly, you can calculate GMR for C. GMR for C. Again, suppose it is C1 and C2. C1, C2. Again, GMR C1 and GMR C2 is going to be same because of the nature of the symmetry. You can calculate either of them. So if you calculate with respect to GMR C1, effective radius of C1 0.7788 into R, and the distance between C1 and C2. Sir, what is the distance between C1 and C2? This is C1, this is C2. It is 3. So it is 3. What is the power? 1 by 2. Then you can calculate GMR for the whole system. The moment you calculate GMD system and GMR system, you can easily write the inductance as 0.2 ln GMD system upon GMR system, and this is millihenry per kilometer. Everybody just tell me in the comment section, are you getting this or not? You guys are not responding. Are you listening? Are you listening? If you are taking these sessions seriously, I know because of experience we are having that these sessions are going to be extremely helpful for your preparation, whether you are preparing for GATE or any other examination, and throughout your life, as far as these subjects what we are discussing, you will never face a problem. I hope you appreciate this. Okay. So this was the case we were talking about this. So let us go beyond this, and we have to talk about the line constant calculation. We have to talk about the line constant calculation. Before this, we have some more questions for bundled conductors. Let us do this. Okay. Just see this question and do it very fast. Bundled conductors, we have discussed it yesterday, na? If a single conductor of radius 4 cm is designed by using a bundled conductor system having 4 conductors in each phase or group, it means initially you are having this conductor, and this conductor is transformed into a bundled conductor having 4 subconductors. We use the name subconductors when we talk about bundled conductors. Okay. So you have these 4 subconductors. Suppose this is R1, R2, R3, R4. And all of them are going to have the same radius. Okay. The radius of each subconductor. Suppose, so this is going to have the same radius. So this is going to be RB, 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 and RB. Okay, I thought there is earthquake. And suppose the radius of this is going to be capital R. So do you know any formula? Yes. The bundled conductor radius is R upon under root N. If you remember this. If you remember this formula. If you don't remember the formula, I will tell you the procedure. Yesterday I have discussed. So directly you can write, what is the radius of this single conductor? 4 centimeter. How many subconductors you are having? 4. So it is under root 4. So it is nothing but 4 centimeter divided by 2. That is nothing but 2 centimeters. What is the answer? 2 centimeters. Very easy question. Another question for bundled conductors. This time I think they may be asking you one question from this area. So there is a hypothetical 2 subconductors bundled system which is again redesigned as the 4 subconductors. If you see, so this is one bundled conductor, it is redesigned in terms of 4 subconductors. If you see the radius, for this one it is R1 and R1, this is R2 and R2, this is R3 and R3. He is asking the value of radius R3. Asking the value of radius R3. But we don't know the value of R1 and R2 also. Maybe some data is missing. Anyways, how to do this? So I told you in this type of question what you have to do. Actually, you have to relate the area. How we are relating the area? Suppose this is having I1, this is having I2, this is having I3, I4, I5, I6. So it means total current for this conductor I1, I2 should be equal to total current here in the 4 subconductors I3, I4, I5 and I6. But you know the current is current density multiplied by area. Now for transmission line, J is constant. So I is directly proportional to the cross sectional area. So you can write A1 plus A2 is equal to A3 plus A4 plus A5 plus A6. But area is again directly proportional to the square of the radius. Yes or no? So from this equation directly you can start, or you can start with the square of the radius just equating the two sides. So I am writing here as, just see this, it means it is R1 square plus R1 square is equal to R2 square plus R2 square plus R3 square plus R3 square. This is 2R1 square. This is 2R2 square. This is 2R3 square. 2 cancelled. It means R3 becomes what? Under root R1 square minus R2 square. If you know R1, R2, you can find R3. Yeah, that is the reason actually. Yesterday there was some time issue. So we started 8 p.m. Okay. But if we start 8 p.m., so it becomes too much late in the night. Okay. So that is the reason. So today we started 6 p.m. Anyways, no problem. I hope people are going to connect. Okay. I hope people are going to connect if they want. No issue. So I hope you're getting this. So we have done one more question for bundled conductors. Let us do one more question. Yes. 3-phase circuit. We have discussed star and delta in the yesterday's session. Na? So from this area also one question can be asked. High possibility. He is saying there is a balanced 3-phase circuit. VAB is given. VAB is given. That is 173.2 angle 0 degree. Voltage is given. Determine all voltage and currents in the star connected load. Very interesting. Star connected load. First thing you understand, if it is a star connected load, yesterday we discussed it. If it is a star connected load, it means what? It means this is A, this is B, this is C. So this is going to be the A phase voltage VAN or simply VA. And this is going to be the line voltage VAB. It means what he is giving you is the line voltage. What he is giving you is the line voltage, yes or no? He is asking determine all the voltage and currents in the star connected load, and the load impedance is also given as 10 angle 20 degree. 10 angle 20 degree. Now suppose if you are having the line voltage, can you write the phase voltage? If you are having the line voltage, can you write the phase voltage? Yesterday we have seen, yes. In case of a star connection, we know that VL is going to lead the line voltage is going to lead the phase voltage by 30 degree. It means if I am writing the phase voltage, suppose I am writing VA. So it is going to be the line voltage. What is line voltage? 173.2. 173.2 divided by under root 3, because we are writing phase voltage. Line voltage is root 3 times phase voltage. So phase voltage is 1 upon root 3 times line voltage. Yes. And its angle is 0. Angle is 0 degree. And here this phase voltage is going to be lagging this line voltage by 30 degree. Lagging this voltage by 30 degree. So can I write VA? If you simplify this, it becomes 100. 100 angle minus 30 degree. Can I write this or not? Say yes or no. Just tell me yes or no. Just tell me yes or no. Just give me a moment. Are you understanding how I am writing the A phase voltage? How I am writing the A phase voltage? Are you able to follow? And the moment you get the A phase voltage, if it is a balanced system, can you write all other phases voltage? Can you write VB? Yes, magnitude is going to be same. The only thing you have to do is B phase is going to have either minus 120 degree or plus 240 degrees. Both the ways you can write it. So if you write adding 240, so it is 240 minus 30, so it becomes 100 angle 210 degrees. This is for B phase. What about C phase? C phase magnitude same. What is the angle? Minus 30 plus 120. So it is 120 degree minus 30 degree. So it becomes 100 angle 90 degree. So you got the A, B and C phases. So you got the A, B and C phase voltages. Now he is asking the current. You have to write the currents also. Voltages you have calculated, because the line voltage is given, you have calculated the phase voltage. Now you have to calculate the current. So because it is a star connection, the line and the phase currents are going to be exactly same. Suppose these are the line currents. The same currents are going to flow into the phases. Say yes or no. So if you are writing the phase current, how you can write it? Very easy. If I am writing the A phase current, it is going to be A phase voltage divided by the load. What is the A phase voltage? It is 100 angle minus 30. 100 angle minus 30. What is the load impedance? The load impedance is given as 10 angle 20 degree. So it is 10 angle 20 degree. If you simplify this, it becomes 10 angle minus 50 degree. If you know IA and it is a balanced one, then you can write IB. IB either you add 240. So if you add 240, it becomes 240 minus 50. So it becomes 10 angle 190. Okay. What is IC? Magnitude same 10. Adding 120, it is 120 degree minus 50 degree. So it becomes 10 angle 70 degree. So you have calculated the line phase currents. Yes, are you getting this, everyone? So this type of questions can be asked in your examination. They may be giving you maybe the line voltage or the phase voltage, maybe star, maybe delta, and they'll ask you to convert it into the line of phase respective values. Let us do one more question. This is little lengthy but very easy to do. Now he is having, there is a balanced positive sequence star connected voltage source where EAB is given as 480 angle 0 degree volt is applied to a balanced delta load. Balanced delta load. So you see what is happening. The source is star connected and the load is delta connected. The situation is something like this. The source is star connected, you can understand. Okay. You can understand this is the source. The source is star connected and the load is delta connected. Now the most fundamental part of this type of problem, how to do this. Suppose this is connected like this. Suppose it is connected like this. My audio, visual, everything is clear? My audio is clear, na? If you know IA, it is a balance. So my audio is clear, okay? So this is going to be connected to this one, okay? And this one is going to be connected to this one. Respective phases you have to connect. So this is, suppose EA, this is EB, this is EC, okay? And suppose these are the line impedances, how you are connecting the source and load, and these are the load impedances. When source is going to be star and this is going to be in delta, the first thing is that you have to convert this delta into star. Then it is going to be easy. So convert this given load, delta load, into star. Suppose this is Z delta, Z delta, Z delta. So convert it into star. So what you will get? So now your load becomes a star connected load. And if it is a star connected load, its impedance becomes what? 1/3 of the per phase impedance in case of delta. 1/3 in case of delta. Okay. I hope you are getting this. Now this circuit becomes easy for you to deal with. Now see what the question is saying. Question is saying Okay, delta load is also there. Delta load is also given. It is 30 angle 40 degree. The line impedance between the source and the load is also given as ZL. That is 1 angle 85 degree. Perfect. For each phase. He is saying calculate the line currents. Now you can easily calculate it. Why? Because if you see this diagram, if you know what is EA, and this is ZL, and I think the source impedance is not given. If the source impedance is not given, you can just ignore it. So if you see this circuit, suppose this is the neutral point, this is also the neutral point of the star. So for calculating the A phase current, what I need is the per phase voltage or the EMF for A phase. Now you see, he is already giving me, in case of a star connected source, he is giving me the line voltage. If the line voltage is given, can I write the phase voltage? Yes. It is 480 divided by under root 3 because I am writing the phase voltage, and angle is minus 30 degree. Angle is minus 30 degree. Like the previous problem. Now you can write the line current IA. It is going to be EA upon ZL plus Z delta upon 3. It means Z star. We have converted delta into star. That star per phase impedance is 1 by 3 of the delta. So I am writing like this. What is EA? It is 480 upon under root 3. 480 upon under root 3. Angle is minus 30 degree. What is ZL? ZL is 1 angle 85 degrees. 1 angle 85 degrees plus, I think Z delta is 30 angle 40. So it is 30 angle 40 degree divided by 3. You have to calculate IA. Just calculate it and tell me what is the value you are getting. Are you getting this? What is the value you are getting? I think you will be getting the line A current as 25.83. I am just quoting it from the reference, 25.83, and the angle is going to be minus 73.78. Minus 73.78. Now the moment you get the line current for A, if it is a balanced system, directly you can write for B. Either you add 240 or do minus 120, same thing. So magnitude is same. If you add, it is 240 degrees minus 73.78. You can just calculate it. What is C? Magnitude is same. Add 120, 73.78 degrees. So you got the line currents, but he is asking what? He is asking the delta load currents also. You have converted delta into star. But for finding the delta currents, delta load currents, you don't need to do any transformation. From these line currents itself, you can directly write. How you can write? So you have the line currents. If you want to write the phase current is going to be line current. What is line current? 25.83 angle minus 73.78. This is the line current. We are finding phase current. So divided by under root 3. And we know that in case of delta connection, the phase currents lead the line currents by 30 degree. So plus 30 degree. Directly you can write. Plus 30 degree. Directly you can write. I don't know whether you are able to follow me or not. If you do so, if you simplify this, you are getting the AB phase current as 14.91. You will not get this much difficult calculation in the GATE exam. This is just for the sake of your understanding. Minus 43.78. Minus 43.78. Now, the moment you get AB phase current, you can easily write BC and CA currents if it is a balanced system. So, BC is going to be 14.91 angle, either you add 240 or you do minus 120, same thing, minus 43.78. Similarly, you can write for CA 14.91 angle 240 degrees minus 43.78 like this. So, you have got the delta load currents also. One more thing he is asking. In the question, one more thing he is asking. He is also asking the voltage at the load terminal. Now, you see this voltage at the load terminal means what? If you know the phase current, if you know the phase impedance, you can easily find the terminal voltage, yes or no? Say yes. You can easily find the terminal voltage. So, terminal voltage, if you are writing at the load side for A phase, it is going to be IAB into Z delta. What is IAB? 14.91 angle minus 43.78 and multiply with this 30 angle 40. You will get the voltage, terminal voltage for A phase. Terminal voltage for the A phase you will be getting as 447.3. 447.3 angle you can check, it is minus 3.78. Minus 3.78. And the moment you get it for terminal voltage for A, you can write terminal voltage for B. Same value. Add 240 or minus 120. So, 240 minus 3.78. You can write terminal voltage for load for C phase 447.3 angle 120 degree minus 3.78 and this is the voltage. Everybody just tell me in the comment section, are you able to follow this or not? Now, nothing can be more than this. For three-phase circuits, they are not going to ask you more than this. If you are able to handle these questions, it means you can do it in the examination also. Examinations calculation are going to be not that much. Okay. Is it clear, everybody? Now, before we proceed for the line constant calculation, let me just talk about some important concepts. Okay, you want me to brief it once again. Okay. Listen. See what we have done. If you understand this question, I think three-phase questions are not going to trouble you. The question is saying that the source is star connected, the load is delta connected. Is it clear? Source is star connected, load is delta connected. Per phase load impedance is given. And the line impedance between the source and the load is also given. Source is not having any impedance. So, the situation is something like this. Source is three-phase star connected, load is delta connected, load impedance per phase is given Z delta and the line impedance connecting the source and the load is also given. Is it clear? The problem is, if one is in star and one is in delta, how you are going to apply the equation? Because we have to write for per phase basis, for one phase at a time. So I have to convert this delta connected load into star connected load. The moment you transform it into the star connected load, you get a circuit like this. Now here the per phase impedance in case of a star connection becomes 1 by 3 times the delta connected load. You know this transformation, star delta, delta star transformation. Yes, Vivek Sadhwani, right. Just convert it into the star. Now he is giving you the line voltage. It means voltage between A and B. What he is giving you? He was giving you VAB, you can say, or EAB, sorry. He was giving you EAB, the line voltage. So first I need this phase voltage. Line to phase voltage, how I am calculating? Line to phase voltage, how I am calculating? If line voltage is given, I am writing the phase voltage as line voltage divided by under root 3, and I know for a star connection, the phase voltage lags by 30 degree with respect to the line voltage. So minus 30 degree. Already in the yesterday's class we have discussed. Now if you know the per phase EMF for A voltage, A phase voltage divided by total impedance of the circuit, ZL plus Z delta by 3. So you can solve it. The moment you get IA, line current, you get IB, IC. Just give 120 degree spacing. The moment you get IA, IB and IC, you can calculate the delta load currents also. Because if you see, the phase current is going to be 1 by 3, 1 upon under root 3 times the magnitude of line current. And in case of delta connection, yesterday I discussed it, the phase currents are going to lead the line currents by 30 degrees. So plus angle 30 degree. If you are not aware about this lead and lag for the star and delta in terms of voltage and current, okay, that needs a separate discussion, because that is a little bit lengthy, because I have to draw the phasor diagram. That's it. Okay. So you can just go to your textbook or some standard textbook, you will get it within no time, even if you can do it yourself also, no problem with that. So I don't think it is going to be that much difficult if you go step by step. Okay. Is it clear? So till now what we have discussed up to the GMD GMR calculation. Okay, you followed the session. Perfect. Actually, yesterday I directly gave you the conclusion part, but how we are saying this, that I have covered in some other session. Maybe if I can give you the link, I have to check it. Okay, I will just put it on my Telegram channel if I get it. Okay, so there is a complete discussion about it. Anyways, so let's proceed. So we have discussed up to this. Now let's talk about the line constant calculation. When I say line constant calculation, you please understand what do we mean in terms of line constant. Why you are calling it line constant? Please tell me why you are calling it line constant. Please understand this, very, very important. If I want to model my transmission line, if I have to model my transmission line, how I am going to model it? How I am going to model my transmission line? So what I am doing, I am going to include all possible phenomena in the equivalent circuit that I am using for my transmission line. That is how I am going to model my transmission line. Yes or no? So I am using 4 parameters: R, L, C and G. R, L, C and G. Good evening, good evening. Yes, Takumi, how are you? Welcome to the session. So what this R is doing here, what R is representing? This R represents the I square R losses in the line. What L is representing? The magnetic field energy. The magnetic field energy is stored in the line. The magnetic field energy is stored in the line. What this C is representing, the electric field energy, is stored in the line. Electric field energy is stored in the line. I hope you're getting my voice. Yes, you're getting the voice. Now, what this G is doing? This G actually represents the leakage current. Sir, what is leakage current? Sir, what is leakage current? We don't know. So, just see this. Suppose this is your transmission tower. Suppose this is your transmission tower. Okay. This is the cross arm. And this is suppose the insulation or insulator string. And suppose this is your live conductor. Now, what is happening? That your insulator string is trying to isolate this live conductor with the tower structure. But whatever you do, because of some reason, always there will be some leakage current. Always there will be some leakage current. So, this is I leakage. Now, this leakage current is nothing but a loss. To model this loss, we are using the conductance. So, this G represents the leakage current of the conductor. Now, you can see when I talk about the resistance, it is rho L upon A. Rho is the resistivity of the material. Once you design your conductor, can you change the material of the conductor? No. So, this is going to be fixed. The moment you design your conductor, resistivity is fixed. Once you design your conductor, your length of the conductor is fixed, or you can change it. It is fixed. So, L is also fixed. The moment you design your transmission line conductor, the cross-sectional area of the conductor is fixed. So, this is also fixed. It means hardly there is going to be any change. There is one possibility of change, that if you talk about AC, because of skin effect, and actually there is one more effect, that is proximity effect. And the result or the conclusion of these two effects is same, that the AC resistance becomes more than the DC resistance. So, because of this skin effect and proximity effect, you can say that there are minor variations in the resistance. Apart from this, there may be variations in the temperature. If there is a variation in the temperature, so you can write RT is equal to R naught 1 plus alpha delta T, where alpha is the temperature coefficient. Yes or no? Alpha is the temperature coefficient. So, if there is changes in the temperature, or if there is a possibility of skin effect and proximity effect, then there will be some minor variations in the resistance. But for all practical purposes, we can say, in case of our transmission system, we will assume that the resistance is fixed. What we are going to do, because of skin effect, proximity effect, or maybe temperature variation, whatever changes are going to happen in terms of AC resistance, we'll take a multiplier, maybe 1.2 to 1.8, and once we multiply our DC resistance of the conductor with this factor, we will assume after this that there are no further changes in the resistance. So, now can I say that R is a constant? Say yes or no in the comment section. Now, can I say R is a constant? Say yes or no in the comment section. Now, let us talk about the inductance. Inductance you are writing as 0.2 ln GMD upon GMR. This is millihenry per kilometer. It means the moment you design your transmission line, is there any possibility you can change the distance between the phases or the size or the radius of the conductor? No, once it is designed, it is finished. It means this is constant, so it means L is also constant. Hello? Say yes or no? What about the capacitance? It is 2 pi epsilon naught ln GMD upon R. I am writing here R, but this is not the physical radius. This is not the physical radius. When I write like this, it means GMR without 0.7788 factor. It means I am saying GMR without 0.7788 factor. It means exactly the same way you were writing GMR for the calculation of inductance. We'll discuss it. Just now we are going to discuss it. Exactly same way you will calculate it, but the only difference is when you calculate the capacitance, in that case you will not use the factor 0.7788. This is the only difference. Why you are not using it? Because in case of capacitance, we talk about electric fields, and for electric field, internal flux linkage is not possible because electric field cannot exist inside a conductor. Yes or no? I hope you understand. Now here also GMD constant, R constant, it means C is also constant. It means quite perfectly you can say that when we talk about our line parameters, whether it is R, L or C, they are constant. There is just one parameter which is not constant, that is G. G we are defining as conductance. G we are defining as conductance. And as I told you, it actually represents the leakage current. Now, because it represents the leakage current, it depends upon two things. Number one, atmospheric condition. Atmospheric condition and the surface condition of the insulator. And the surface conditions of the insulator. Surface conditions of the insulator. I hope you are getting this. Because if the weather is not good, if a lot of moisture is there in the weather, then the possibility of leakage current from the live conductor towards the tower foot is going to be very high. If the surface of the insulator is not in a good condition, if it has roughness, if it has deposition, then also the possibility of leakage current is very high. So because of these two reasons, G is not a constant, but for most of our practical purposes, we are assuming this is also constant. So you can say that when we talk about the line constant calculation, now you understand why we were calling them line constant. Why we were calling them line constant. Is it clear for everybody? Say yes or no. Just tell me in the comment section, are you getting this? Yes or no? Why we are calling these parameters as constant. Now, if you see most of the time in your GATE examination, they will not be asking you in terms of resistance and conductance is not required. Most of the time they will be asking you in terms of the inductance or the capacitance. So that is the case I have to discuss. So let me just talk about case 1, and I am talking about single phase 2-wire system. Single phase 2-wire system. What do we mean? Single phase 2-wire system. Now you see this. So this is A and this is B. It is a single phase forward conductor and return conductor. Okay. Suppose the distance between them is like this. Center to center distance is d. Suppose their radius is also given. So this is r1 and this is r2. This is r1 and r2, or simply r you can say. Okay. So if I talk about the inductance, the total inductance, or we also call it loop inductance, this is equal to LA plus LB. Do you understand why we are writing it like this? Why we are writing it like this, loop inductance or total inductance? Simple reason, simple reason. See this. See, simple reason, simple reason. What is the reason? If you are saying, sir, this is the circuit, sir, this is the forward line, this is how the load is connected, and suppose this is the written path. So if this is LA and this is LB, and he is asking you what is the total impedance, sorry, total inductance. So for this loop inductance, you have to add the inductance of A and B. That is the only case possibility. Say yes or no. That is why we are writing loop inductance. Now you see. Anyways, it means I have to calculate inductance for A separately, inductance for B separately, and then I can add them up. Suppose I am writing and I am trying to find the inductance for A phase. Now A phase inductance I will divide into two parts. Inductance because of internal flux linkage and inductance because of external flux linkage. Sir, what do we mean in terms of internal flux linkage and external flux linkage? I will show you external flux linkage, internal flux linkage, you can understand. So when you talk about the current which is passing in this conductor A, what is happening? Because of current passing in this conductor, suppose the current is passing into the plane of the board. So what is going to be the magnetic flux lines? Apply the right hand thumb rule. If thumb is going into the plane of the board, the movement of the finger will give you the direction of magnetic flux. So that is going to be what? Clockwise. So what you are getting magnetic flux like this. Magnetic flux like this. Are you getting this? So this is how you can define the external flux. Internal flux means those part of the flux which is inside the volume of the conductor. Flux which is outside the volume of the conductor, you can call it as external flux for most simple understanding part. Okay, just to make you understand. Now, if you calculate the internal and external inductance, what you are getting? The internal inductance you are getting as mu naught mu r upon 8 pi. Mu naught mu r upon 8 pi, and this is Henry per meter. When you calculate the inductance because of external flux linkage, I am not going to the derivation part because that will take a lot of time. Okay, I hope you have gone through that, and I am just going to make you understand this. So the inductance because of the external flux linkage comes out to be mu naught mu r upon 2 pi, and this is ln d minus r2 upon r1. D minus r2 upon r1, and this is again Henry per meter. This is again Henry per meter. There is one important thing that you have to understand, and lot of people do mistake in this. When I am writing mu r, relative permeability, this relative permeability is different from this relative permeability. When I am talking about the internal flux linkage, I am inside the conductor, so mu r is going to be the mu r of the conductor material. This mu r is the mu r of the conductor material. But when you are talking about the external flux linkage, you are outside the conductor. It means you are talking about the mu r or the relative permeability of the medium in which conductors are placed outside the conductor. So this mu r is the relative permeability of the medium. Don't do mistake in that. Don't do mistake in that. Okay, why we are getting D minus R2? Why we are getting D minus R2? You can see the external flux linkage. D minus R2 means total distance is D. If you subtract R2, you are till now, this is, you are here. You are here. You are here. Are you getting this? So external flux linkage is going up to D minus R2. So you are getting D minus R2. And this is R1. No problem with that. Now you see, most of the time D is going to be very, very large in comparison to R1 or R2. So instead of writing like this, you can directly write as LA external as mu naught mu r upon 2 pi ln D upon R1 or simply R. Okay, whatever you want, Henry per meter. I hope it is clear. Now you see, sometime in our life, something happen without any effort. We don't make any effort and we get things. This happens with everybody. But we don't know what is going to happen. If you see by chance what is happening, if you talk about the mu r for the air medium, this is 1. And mu r for the aluminium is approximately 1. So if you are using the aluminium conductor, aluminium material, you are saved. If the conductor is made of another material, maybe copper or maybe other material, then you have to be very careful, because then you cannot use that formula which we are using everywhere, 0.2 ln GMD upon GMR. You cannot use that. That is only possible if you are having air and the aluminium. So what happens when you write the inductance for A phase? You are writing mu naught, mu r has become 1 for the conductor material is aluminium, mu naught mu r upon 8 pi plus mu naught mu r air medium again 1 upon 2 pi, and this is ln D upon R or R1, whatever you want you can write, and this is Henry per meter. Now what we do, we take mu naught upon 2 pi as common. So what you get, 1 by 4 plus ln D upon R1. This is Henry per meter. Simplify this. So I am writing LA as mu naught upon 2 pi, and I am writing this 1 by 4 as ln e raised to the power 1 by 4 plus ln D upon R1. This is again Henry per meter. Just add them up or combine them. So it becomes mu naught upon 2 pi, and it becomes ln D e raised to the power 1 by 4 upon R1, and this is Henry per meter. Now I will bring this e raised to the power 1 by 4 in the denominator. So I will get LA as mu naught upon 2 pi ln D upon R1 multiplied by e raised to the power minus 1 by 4 Henry per meter. Now this e raised to the power minus 1 by 4 is 0.7788. The factor we were discussing number of times. How this factor is coming, this is the reason. And it is coming because of the internal flux linkage. It is coming because of the internal flux linkage. Say yes or no. Say yes or no. Are you getting this? Are you getting this or not? Yes? Why you are getting this? This is the answer. So now you can write the inductance for A conductor as mu naught upon 2 pi ln d upon r1 dash. What is r1 dash? r1 dash is nothing but effective radius or GMR, where you are writing r1 dash as 0.7788 into r1. Babu, you are getting this or not? Tell me. And again, this is Henry per meter. Let us put the value of mu naught upon 2 pi. So it becomes how much? Mu naught you can write as 4 pi 10 to the power minus 7. Mu naught value is 4 pi into 10 to the power minus 7. This is 2 pi. This is ln d upon r1 dash Henry per meter. This is 2. What I am going to do, I will take 1 10 to the power minus 1 and multiply it to 2. So it becomes 0.2. Then the remaining one is 10 to the power minus 6, which I will distribute to Henry and meter so that they become millihenry, and 10 to the power minus 3 coming down, it becomes kilometer. So this is the final expression you are getting for the inductance calculation. Everybody tell me in the comment section, are you able to get this or not? Now this is one of the most general expression for writing the inductance, which if you are writing in terms of GMD and GMR, then you can write 0.2 ln GMD upon GMR, and this is millihenry per kilometer. This is extremely important to remember the unit. Don't forget it. The moment you get this, can you similarly write? I'm not getting a response. I don't know whether you are able to follow me or not. LB becomes 0.2. Similarly, you can write, I'm writing it for B. I'm writing it for B. So similarly, you can write LB as 0.2 ln. It is going to be D minus R1 R2 dash, because D is very, very large in comparison to R1 or R2. So simply we are writing D. So it is not D minus R1, it is D. And again, this is millihenry per kilometer. So voltage L total LA plus LB. This is 0.2 ln D upon R1 dash plus 0.2 ln D upon R2 dash. And this is millihenry per kilometer. Now suppose if R1 and R2 are same, then it will just add up. Then in that case, the total inductance you can directly write as 0.4 ln D upon R dash millihenry per kilometer, and you can say if R1 and R2 are same and equal to R. This is the case for a single phase 2-bar line. Now if you talk about a 3-phase line, for a 3-phase system, if you are writing A phase inductance, how you are writing? 0.2 ln GMDA upon GMRA. This is millihenry per kilometer. If you are writing for B phase, you can write it as 0.2 ln GMDB upon GMRB, this is millihenry per kilometer. If I am writing for C, it is 0.2 ln GMDC upon GMRC. This is millihenry per kilometer. Sometimes for a three-phase system, they are asking the per phase. Per phase. For that case, you can take the average. You can take the average. Okay. Find LA, LB, LC separately. Then take the average. This is one method. There is one more shortcut method. Approximately will. Vivek Shadwani is asking, so can you summarize only important formulas for this year GATE? Definitely we have the separate session for formula revision actually. In the very starting part of the discussion, I told you that we have planned so many things for your upcoming GATE 2026 examination. So if you are a serious candidate for GATE 2026, we are right now having the Maha Revision. It means in a very exhaustive manner, we are going to complete the theory portion with some understanding based questions. Then we will come up with the PYQs, some important previous year questions, maybe 10, 15, 20 years. After that, we'll come for formula revision also. I don't think that today we can discuss fault. Right now, we are discussing transmission line. Okay. So the third lecture, the third part that we are going to have, in that we will discuss fault analysis. Okay. Why you are so much worried about fault analysis? Very small portion. Okay. And even you and me don't know, we both don't know whether you will get a question from fault analysis or not. See, this is the problem. You don't take any part of your syllabus as lightly. Otherwise, there will be a problem. GATE is not about remembering the formulas. GATE exam is about understanding the fundamental concept. If you understand the concept, nobody can shake you. At least 50 plus marks easily you can get in GATE examination if you simply understand the concepts. If you are not a very, very super human or rocket science student, if you simply understand the basic things, basic concepts, no need to remember big formulas, at least 50 plus marks you can easily get. The problem is with the negative marks. Don't take it lightly, okay? Whatever we are discussing, you will see after the examination that there will be questions from this area, what we are discussing already. I know this. There has been 15 years, I know this. Okay. Anyways, so we are discussing like this. Now there is a problem. Okay. There is a problem in case of a three-phase system, there is a problem. Just give me a moment. Yes, in case of three-phase system, there is a problem. What is the problem? The problem is, suppose this is your transmission line. Understand the problem. Something important, it's not like this only. Suppose this is your transmission line. This is A, this is B, and this is C. Suppose at this side you have the source or the generator, and it is a balanced three-phase supply. Okay. Suppose these A, B, and C phases are also identical in terms of its design. At the load side, the load is also a three-phase balanced load. Three-phase balanced load. I am saying that the source is balanced, supply side is balanced, the lines or the three-phase system that is also having similarity, exactly same. Even the load side is also balanced. Still there is a possibility that what you are getting here is not balanced, you may get unbalanced voltage and current at the load terminal. What is the reason, sir? The reason is the very positioning of A phase and B phase and C phase. A phase and B phase and C phase. The positioning of A with respect to B and C is different from the positioning of B with respect to A and C, and the positioning of C with respect to A and B. Are you getting this or not? So because of this reason, what is happening? The magnetic flux linkage is going to be different for different positions of the conductors of A and B and C. And when the magnetic flux linkage is different, when you model the transmission line, the reactance you are going to use, that is also going to be different, inductive reactance. When that is different, it means what you are getting at the load side is not balanced. What you are getting at the load side is not balanced, it means there will be a problem. Problem of stability, losses will be there, so many problems. So to remove this problem of unbalanced nature of the system, even if the source is balanced, the load is balanced, the lines are symmetrical, we go for transposition. We go for transposition. As the name indicates, transposition means after every 1/3 length, we change the position of the conductor with each other. After every 1/3 distance of the transmission line, we change the very position of the transmission line conductors so that each conductor is going to occupy all the positions for equal distances. So the effect of magnetic flux linkage is gone. Yes or no? If you are going through the same phase through which I am going, then you will understand my problem. Yes or no? So you can see this. So you see, if this is A, this is B, and this is C. So now this is A, this is B, and this is C. Now A will become at this position, B will go to this position, and C will come to this position. So now you can see that for equal distances, each phase or conductor phase is going to have similar position. So now the magnetic flux linkage problem is gone and the problem of unbalancing is also gone. Are you getting this? Now, because of this reason, if you have a transposed line, what I am saying, just keep my words very carefully. If you have a transposed line, three-phase line, in that case, LA, LB and LC are going to be exactly same. LA, LB and LC, they are going to be exactly same. Is it clear for everyone? Say yes or no in the comment section. Are you able to follow this? Are you able to follow this? Okay. So this was all about the inductance calculation. Okay. So let me just now talk about the capacitance calculation. Capacitance calculation, they can also ask you questions. Capacitance calculation, let us again have the case of a single phase two-wire system. A single phase two-wire system. Single phase two-wire system. So again the situation is going to be something like this. This is A, this is A, this is B, okay. This is a point P which is exactly midway between A and B. So this distance is D and radius you can understand, suppose this is R and this is R or R1, R2, whatever you want you can take, okay. Now one thing you understand that when we show this diagram, the conductor A and B, they are not circles, they are cylinders into the plane of the screen. So this point P is not just a point, it actually represents a plane, a two-dimensional plane which is equipotential, and on this plane at all the points the potential is zero. Because when we talk about capacitance, we have to talk about electric field. For electric field, we have to talk about potential, and we cannot talk about potential without a reference. So while we talk about the calculation of capacitance, we have to define what is the reference. So that reference is nothing but this equipotential plane which is passing through this point P. I hope you are getting this. So when I write the capacitance, suppose I am writing the capacitance, suppose like this. With respect to this neutral point or reference point, so this is CAN. It means the capacitance of conductor A with respect to the reference point. Similarly, I am writing CBN, that is the capacitance of conductor B with respect to N. So now if I write the expression CAN or CBN is nothing but 2 pi epsilon naught upon ln d upon r. Simple, you can say it is farad per meter. If you talk about the line capacitance CAB, so if you see CAB is going to be the series combination of AN and BN. In series connection, the capacitance are divided, yes or no? So you can write it is 1 by 2 CAN or 1 by 2 CBN. So it is going to be pi epsilon naught upon ln d upon r, and this is farad per meter. This is farad per meter. Is it clear, everybody? Are you getting this? So when you are talking about the line capacitance, then you have to use this formula. If you are talking about phase capacitance, then you have to use this formula. Be very careful. Okay. Now suppose you are talking about the general expression for the capacitance. So this is going to be 2 pi epsilon naught epsilon r upon ln GMD upon r. But please remember, we are writing it R, we are not writing GMR because GMR is actually not defined for capacitance calculation. Because when you say effective radius, that effective radius concept is coming because of the factor 0.7788. But in case of capacitance, we have the electric field, and electric field cannot be present inside the conductor. It means there cannot be any internal flux linkage as far as the electric field is concerned. It means that factor is not going to come here. So this R is actually this R is actually GMR, what you were calculating in case of inductance without the factor 0.7788. Rest everything is same. Rest everything is same. I hope it is clear. Is it clear, beta? Tell me yes or no. So this was about the capacitance calculation. If you are writing it for 3-phase, then the same thing what we have done for the inductance that you can do. Okay, you can write it like this, farad per meter. Okay. Now let us go beyond this. Let us go beyond this and let us talk about some important concepts. So let me just first talk about the skin effect. I hope everybody is comfortable with the skin effect. Say yes or no. Everybody is comfortable. If you are comfortable, then my task is going to be easy. Otherwise, it will take some time. So suppose you are having a conductor. You are having a conductor like this. Okay. And if anyone goes from the surface of the conductor towards the inside or the core, what they are going to get? What they are going to get? See what is happening. If I am defining the current density J as J naught e raised to the power minus d upon del. This is the current density, how we are defining it, that we are starting from a value and after that there is exponential decrease. Okay, this is how we see the current is going to behave. So suppose you are standing at the surface of the conductor and the current is going to reduce like this. You are standing at the surface of the conductor and the current is reducing like this as you go inside of the conductor, as you go inside of the conductor. So actually this distance from this part we are defining as d. And this is not just 2 points. You imagine that cross section area of the conductor at each point on the surface. If you are going from surface towards the core, the same thing is happening. The same thing is happening. Are you getting this? Everybody tell me in the comment section, are you able to follow this? If you are aware about the skin effect, then I will just do it very quickly and you can relate it. So if you see how I am defining this, this is called skin depth. Skin depth. How I am defining this skin depth? If d is equal to del, what is going to happen? If d is equal to del, then J becomes what? It is 0.367 times J naught. This is J naught. This is J naught. It means when the current density, you are starting from the surface of the conductor and you are going inside of the conductor. The moment the current density reduces to somewhere around 36.7% of its surface value. It is 36.7% of its value at the surface. It means that is the distance from the surface of the conductor up to which effective current is present. So you are defining del as distance from the surface of the conductor up to which effective current is present. I am not saying no current is present, after which, up to which, I am not saying all the current is present. I am saying effective current is present. It means beyond this del also there is some current. up to which effective current is present. Effective current is present. It means, listen, if you go up to 5 del, beyond this, no current is present. Beyond this, no current is present. No current is present. Arey Baba, tell me yes or no, are you getting this or not? Okay. So what is happening? What is happening? If you see your conductor, the current is distributed like this. For AC currents, the currents are having a tendency to crowd near the surface of the conductor. And if you go to the core part of the conductor, there is hardly any current, very less current. So starting from the surface of the conductor, this very distance up to which effective current is present, this we are defining as del. Okay? And this del is equal to 1 upon alpha, where alpha is, we'll discuss later on, it is the attenuation constant. It is the attenuation constant. And alpha, you can write it as sigma omega mu by 2, where sigma is the conductivity, mu is the permeability, okay, and omega is frequency. Yes or no? Now you tell me, if del is going to be more, listen very carefully, if del is going to be more, then skin effect will be more or less? If del is more, if del is a large value, see, skin effect simply means the amount of non-uniformity within the cross section of the conductor, how much non-uniformly current is being distributed across the cross section of the conductor. So if del is going to be more, the non-uniformity is less, it means the skin effect is also less. If del is going to be small, it means non-uniformity is very high, it means skin effect is also very high. It means you can relate skin effect and skin depth, and you can say that skin effect is inversely proportional to skin depth. Are you getting this? It means what? 1 upon del, and this is directly proportional to 2 upon, sigma omega mu upon 2. Yes or no? It means what? It means when the skin depth is reducing, it means non-uniformity is increasing. It means non-uniformity in the current distribution is increasing. When skin depth becomes less, it means current is concentrated just near the surface of the conductor. And suppose skin depth is 0. If the skin depth is 0 and it is for ideal conductor, Arey Baba, you are saying skin depth is inverse of alpha. Alpha is this. So what is del? Del is under root 2 upon sigma omega mu. Now if you are having ideal conductor means that conductivity is infinite. If the conductivity is infinite, it means del becomes 0. It means for an ideal conductor, the AC current has a tendency to be available only on the skin of the conductor or the surface of the conductor. Are you getting this? And that is the reason it is called skin effect, my dear friend. So you understand that if this skin depth is going to be small and small and small and small, it is getting smaller, it means the non-uniformity in the current distribution across the cross-section area of the conductor is going to be increased. It means what? Skin effect will increase. Skin effect will increase, my dear friend. And what are the possibilities how skin depth is reducing? Skin depth can reduce if conductivity is high, if frequency is high, or mu is high. Are you getting this? Everybody just tell me in the comment section, yes or no. Are you getting this or not? There was one question maybe in GATE 2022 or 2021, I don't remember, on Ferranti effect. So let us discuss Ferranti effect. This year, I have a gut feeling that you can get a question from Ferranti effect. So let us talk about Ferranti effect. If I talk about Ferranti effect, what happened 1890, it was 1890 when S.Z. Ferranti, he observed something extremely interesting. What is that interesting? In general, when we talk about any electrical circuit, what we say that current will always flow from a higher potential to a lower potential. This is the most common understanding we have for electrical circuits as far as KCL, KVL is concerned. But this fellow observed something very unique. He observed that if you have a transmission line, or you can say simply a circuit, if it is a light load or no load condition, the receiving end voltage magnitude was higher than the sending end voltage. Are you getting this? What he observed, if you have a generator or sending end, and suppose this is the receiving end and this is the load side, suppose this is generator, so this is Vs angle del, and suppose this is Vr angle 0. What he has observed that if it is a light load, or no load condition, in that case the magnitude of receiving end voltage is higher than the sending end voltage. This effect he was calling as Ferranti effect. Now let us understand why this effect is happening. Suppose this is the generator side, okay. Suppose this is the case. We are saying it is no load, so let us leave it like this, okay. Or suppose it is light load condition, so let us connect the load so that you can understand. Now, this current is I, okay, this is R plus JX. This is nothing but the impedance of the line, you can say. Yes or no? Impedance of the line. Now, suppose if you are writing this particular equation, by using the sending end voltage and the receiving end voltage, how you can write it? Yes? How you can write it? पापा बेटा बाहर गए. हाँ, पापा फोन पे बात कर रहे हैं. So suppose if I want to write the relation between the sending end voltage and the receiving end voltage, how I can write? I can write Vs is equal to Vr. Suppose I am taking Vr as the reference voltage. So this is Vr angle 0 degree. So what I am getting as Vr plus the current and multiplied by the impedance. Yes or no? But if it is a light load condition, this current I is going to be a charging current. or we call it capacitive current, or it is a capacitive current. Now, if it is a capacitive current, how you are writing this current? This current I am writing as VR multiplied by j omega c. Yes or no? Are you writing this or not? By using the equivalent circuit of the transmission line, remember, by using the equivalent circuit of the transmission line, VR into j omega c. So you can put this in this equation. You can put this in this equation. So what you are getting, Vs as VR plus, what is IR? It is VR j omega c, and Z is how much? Z is R plus j omega L, you can say, yes or no, j omega L. If you want, you can simplify this a little bit. So it becomes how much? VR, if you multiply it, it becomes minus j square becomes minus. It is again VR, and this is I think omega square LC. Omega square LC plus we are getting J, okay, J omega CR, and this is VR. Okay. Now, if we assume that it is a lossless line, now for a lossless line, you can say R is going to be 0. If R is 0, this part is 0. Now, just focus on this part. Vs is equal to VR minus VR omega square LC. It means what? VR positive, omega square positive, L positive, C positive. It means this whole number is a positive number. It means you are getting receiving end voltage, adding something to Vs. It means you can prove that for a charging current or capacitive current in the line, the capacitive current in the line, the receiving end voltage becomes higher than the sending end voltage. I hope you are getting this. I hope you are getting this. Now, if you see, let me just talk about the one more part, one type of question which was asked in 21 or 22. Just give me a moment, I am searching that question. Just give me a moment. Yes. I remember the question, okay. I remember the question. The question was, see, if I draw the phasor diagram, you will understand it quickly. Suppose we are taking the receiving end voltage as the reference. This is the receiving end voltage, okay. The line current is capacitive or charging. Suppose it is capacitive or charging. So the line current is leading this voltage by 90 degree. Leading this voltage by 90 degree. So this is IC. Now, if you want to get sending end voltage, you have to add the drop of resistance and reactance of the line with this current. Yes or no? So how you are going to add them up? VR plus IC into R. See this. VR plus IC into R. This is IC in the direction of IC into R because this is resistive drop. Now it is JXL. JXL drop is going to be like this. JXL drop is going to be like this. So this is IC into XL, you can say, the series reactance of the line. Now what you are getting is your sending end voltage. What you are getting is your sending end voltage. This is Vs. I hope you are getting this phasor diagram. Now, if R is 0, here R is not 0. Suppose R is 0. If R is 0, what is going to happen? Just see this. If R is 0, this is when R is not 0. Now, if R is 0, I am taking this case. If R is 0, what will happen? See very carefully. This is the receiving end voltage. This is the line current, which is a charging or capacitive current. So, leading the voltage by 90 degree. This is VR. This is I or IC. Now, there is no resistive drop because R is 0. So, only this reactance drop is there. Sir, how much is this reactance drop? Something like this. Now, this is IC into XL. So, what is the sending end voltage, sir? Sir, this is the sending end voltage. Now, you understand. This is sending end voltage, this is receiving end voltage. Now, you understand why the sending end voltage is less than. Vivek Shadwani is saying, sir, is there a transformer impedance that represent transformer while considering connected with transmission line? It depends how the question is framed, na? You are asking, or what you want to ask actually, I am not getting. You are asking for this particular part, or in general you are asking? So, you are getting what is the reason. So, this drop, and this drop is because of two things. This drop is because of two things. This drop is responsible for Ferranti effect. And that drop is because of two things, IC into XL. Line charging current. So, the first requirement of having the Ferranti effect is that there should be a capacitive current. There should be a capacitive current. Okay, wait. So, let me just see what he is asking. Is there a transformer impedance that represent transformer while considering connected with? I think yesterday also I have discussed, if you are using the per unit system, your transformer becomes just like an impedance. That is what we are doing in the reactance diagram. So, IC is the line charging current. Now, you have the line charging current in your line if you have the no load or light load condition. No load or light load condition, because when load is high, then most of the power or the current is going to be real. Yes or no? Because ultimately we are delivering the real power. This XL is what? XL is the inductive reactance of the line. It means Ferranti effect you will observe only and only when the line charging current is capacitive, first condition, and the second condition is that line charging current must pass through the inductive reactance of the line. Yes or no? So, in 2022 or 2021 maybe, they were asking that what is the difference in the sending end and the receiving end voltage. Can you tell me what is that? Yes, ICXL. So, they were asking the voltage rise. So, voltage rise was ICXL. But this IC is not simple IC, because now you are calculating the voltage rise. We have to take the average current. We have to take the average value of this IC current. So, this is 1 by 2, okay, 1 by 2 VR, and this is omega C into L. Why I am writing omega C into L? I am just talking about magnitude, so J is gone. It is omega C, and C actually we have written per unit length. So, I am multiplying with this L so that you get the total capacitance. What is this XL? XL you are writing as again omega L into L. So, if you simplify this, you will get 1 by 2 VR omega square LC, and this is L square. So, they have actually asked a direct question on this formula. They have actually asked, I think maybe 22 or 21 in GATE examination, they have directly asked a question based on that how much voltage rise you can expect. They have given the receiving end voltage, L, C and length of the line. Just note it down. Everybody just tell me in the comment section, are you able to follow this? Everybody just tell me in the comment section, are you able to follow this? Say yes or no. Now let me just talk about one more phenomena that is also important from your GATE examination point of view this time. Okay. GATE examination point of view, it is important. That is radio interference. Can be asked. Radio interference. Sir, what is radio interference? See, when we talk about the transmission line, our transmission line is actually going for a very long distances. So generally what we used to do, that the telecommunication lines or the channels are generally laid down along with the transmission line. Now because the telecommunication lines are getting very close to our transmission line, there is a possibility of magnetic flux linkage with these telecommunication lines because of the current in the transmission line conductor. And whenever there is a magnetic flux linkage with the conductor, there will be some induced EMF. Are you getting that? Okay. So that causes the interference. Okay. Earlier time when you pick the phone as that is nothing but the radio interference, you can see in the most simple way. Okay. So what is this radio interference? Let us try to understand. So suppose this is your transmission line conductor and this is telecommunication. Okay, telecommunication. Suppose this is A and this is T. Okay. Now suppose it is having some current I. It is having some current I. This current is going to have some flux. That flux will link with the telecommunication line or the channel. Okay. So I want to know the induced EMF. The induced EMF is going to be d xi by dt, where xi is the magnetic flux linkage and d by dt is the rate of change. Or you can also write it like this, m di by dt. As you write for inductance L di by dt, similarly you can write. Why not? Theoretical question can also be asked. And if you understand the concept, whether it is theoretical one or whether it is numerical one, it hardly matters. Most of the questions, if you talk about MSQs, multiple select questions, most of the questions you will see they are theoretical question only. Okay. Now suppose if I write the RMS value, so this is going to be m omega I. Yes or no? M omega I. Now what is Mi? What is Mi? Xi, that is the magnetic flux linkage, is nothing but m into I. So you can write the RMS value of the EMF induced in the telecommunication line is nothing but Mi is xi. So this is nothing but xi into omega. Xi into omega. This is the whole logic. This is the whole logic. Suppose if we take the example of, single phase two-wire system. Suppose if we take the example of single phase two-wire system, where the situation is something like this. Okay, suppose this is your, Okay, these are transmission lines and these are the telecommunication channels. So we are calling them as T1, T2, and this we are calling as A and B as the forward and the return conductor. Now let me just draw the distance between them. So if you see this distance and this distance, I am defining this as D1, this is D2. Similarly, I am defining this as D1 and this is as D2. Okay. So suppose I want to know that what is the net induced EMF in this telecommunication line. So first I will calculate the flux linking with T1, then flux linking with T2, then I will see the difference. So flux linking with T1, how I am going to write it? Just see it very carefully. When you write flux linking as M into I, sir, what is M? Sir, M is 0.2 ln 1 upon D. D is the distance. Just now what we have seen in case of inductance. It means you can write the flux directly as 0.2 I ln 1 upon D. So this equation I am using here. So if I want to write the flux linkage with telecommunication channel T1 because of the conductor A having the current I and conductor B is having the current minus I. It is having the current minus I. So suppose you are writing for conductor A. So this is going to be how much? This is going to be 0.2 I, okay, ln, what is the distance? It is D1, 1 upon D1. If you are writing for T1 with respect to B, so it is minus I, so it is 0.2 I and this is ln 1 upon D2, ln 1 upon D2. Yes or no? It means you can write phi T1 is 0.2 ln, sorry, it is 0.2 I ln D2 upon D1. Say this is equation number 1. Similarly, you can find the flux linkage with T2. Flux linkage with T2 is going to be, because of conductor A, it is 0.2 I and the distance is D2. 0.2 I ln 1 upon D2. Now on T2, because of B, that is minus I, it is D1. So it is minus 0.2 I ln 1 upon D1. So if you combine this, it becomes 0.2 I ln D1 upon D2. Say this is equation number 2. Now the difference in the flux linkage is going to be the one which decides the EMF induced. Yes or no? This is 0.2 I ln D2 upon D1. This is minus 0.2 I ln D1 upon D2, or if you simplify it, it becomes 0.4 I ln D2 upon D1, and this is the flux. If I multiply this flux with omega, I will get the RMS value of the EMF induced. So the RMS value of the EMF induced is going to be omega multiplied by 0.4 I ln D2 upon D1, and it is millivolt per kilometer. Very important formula. Very important formula. This year there is a possibility you may get a question on this. This year there is a possibility you may get a question on this. Just tell me in the comment section. Are you able to follow this? Vivek, tell me. Yes, everyone. So let us do one question on this particular topic. You may get a question on this. If you understand the concept, I think that question is going to be just very easy for you. Just very easy for you. एक सेकंड रुकना भाई, मेरी श्रीमती जी मुझे कॉल कर रही हैं, देखें कोई खास बात तो नहीं है. So let me just show you the question. Hello. हाँ बताओ, सेशन में तो लिंक भेज दिया, लाइव में देख लो उसमें ना. हाँ तो अभी तो बच्चे बैठे हैं ना. Okay. What I was saying, yes. Let us see the question. Let us see the question. See this question. Find the RMS value of the EMF induced in the communication conductors for a single phase two-wire system as shown in the figure. So can you directly write? Can you directly write? I think there is some data is missing in this question. Let me just give you the data also. Otherwise, how you are going to solve it? Yes, data is not given actually. So just take the data. D1 is 2.5 meters. D2 is 3 meters. Current is, and it is the RMS value is given 100 amperes. It is the RMS value. And if you talk about frequency is 50 hertz. Now just now the case we have discussed for the single phase two wire line, you can directly write the induced EMF, yes or no? 0.4 into I. What is I? 100. Okay. ln D2 upon D1. What is D2? 3 upon 2.5. Okay. D2 upon D1. And multiply this whole with omega, that is 2 pi f. Finished. This is the answer. Just put the values, you will get the answer. Everybody is getting the radio interference or not? Tell me yes or no. See, if you don't respond, then it is a little difficult for me to understand whether you are able to follow me or not. Say yes or no. Anyways. Okay, this we'll do later on. So this was what we wanted to discuss before we proceed further. I hope it is okay for all of you. So till now we have discussed up to radio interference. Okay. So now we are ready to go for the performance analysis of our transmission line. But before that, we need a very small tool, that is ABCD parameters. Are you ready for that, everybody? You must have read it in your networks subject. So I am not going into depth, just I am introducing how much I need, that will take. So ABCD parameters, which are also called as transmission parameters, and these are very useful when you have cascaded network. Cascaded network. Sir, what is cascaded network? Cascaded network means when the output of one network becomes the input of another network. If the output of one network becomes the input of another network, in that case you can write the ABCD parameters for one network and ABCD parameters of the second network and just multiply them, you will get the equivalent ABCD parameters of the combined network. That is the case very useful for cascaded network, yes or no? So if you have a two-port network like this, suppose you have a two-port network like this and you are writing the ABCD parameters, okay, and these are the sending end voltage and current, and these are the receiving end voltage and current. Sending end voltage and current and receiving end voltage and current. How I am writing the sending end voltage? AVR plus BIR. Sending end current CVR plus DIR. If you want, you can write it in the matrix form also. VSIS, and this is A, B, C, D, and this is VRIR. This is VRIR. Is it clear? This is VRIR. Yes or no? To understand what is this ABCD, let us go for some basic conditions. You know that one basic condition is that we go for open circuit. When we go for open circuit condition, open circuit means the receiving end is going to be open circuit, okay? So receiving and open circuit means there can be no current. There can be no current. If IR is 0, can you tell me what is going to be A? A is going to be Vs upon VR when IR is 0. This is called, my friend, reverse voltage gain for open circuit. Now if you talk about second equation, if IR is 0, what is C? IS upon VR. IS upon VR, and this is also when IR is 0. When IR is 0. So this is going to be what? This is transfer admittance. This is transfer admittance for open circuit condition. For open circuit conditions. Is it clear? You can divide this, so you will get A by C. What is A by C, bhaiya? VR same, IR 0 condition same, so it is Vs upon Is. It is Vs upon Is. IR being 0, that is the open circuit condition. This is nothing but ZOC, or it is also called as Z11. So this is called driving point input impedance at open circuit. Now similarly, you can write for the condition of short circuit. When there is a short circuit condition means the receiving end voltage becomes 0. The receiving end voltage becomes 0 means it is short circuited. So VR 0 means what? What is B? Vs upon IR. What is B? Vs upon IR when VR is 0. What is this? What is this? Transfer impedance in case of short circuit. Second equation, if you put VR is equal to 0, if you put VR is equal to 0, what is D? IS upon IR. What is D? IS upon IR, and this is VR is equal to 0. Now if you see, this is nothing but the reverse current gain. This is nothing but the reverse current gain in case of short circuit. Again, you can divide B and D. What is B and D? Again, IR same. VR0 condition same. It is VS upon IS. It is VS upon IS. VR is equal to 0. So, this is the driving point. Driving point input impedance in case of the short circuit. So, we are defining it as ZSC or Z22, you can say. So, if you see the characteristic impedance, we'll discuss it later on. We'll discuss it later on, characteristic impedance. So, that you can define as, characteristic impedance you can define as ZOC into ZSC. So, this is actually coming as AB upon C into D. So, if you know the ABCD parameters of a line, you can also calculate its characteristic impedance. What is characteristic impedance? We'll discuss. What is characteristic impedance? We'll discuss. Okay. I hope you are getting this. A, B, C, D. So, you understand how you are going to do this. Now, let me talk about some standard form so that you can use it later on when you are writing the ABCD parameters. So, if you are having case 1, suppose this is the case. Can you write the ABCD parameters? Yes, it is 1, Z, 0, 1. Case number 2. Can you write the ABCD parameters for this? Yes, it is 1, 0, Y, 1. Can you write the ABCD parameters for case number 3? This is Z. So, now the ABCD parameters will be 1, 0, 1 by Z, and this is 1. These three you can use for getting the most of the cases as far as our particular subject is concerned. Is it clear? Are you getting this? Vivek, Beta, and so many other candidates, can you tell me in the comment section? Okay. So, now let us start with the short transmission line. Short transmission line. Short transmission line, how we are defining the short transmission line? When the length is less than 80 kilometer, when the voltage is less than 20 kilovolt, okay. So, we are saying it is short transmission line. To represent our line, we are using the lumped parameter model. Lumped parameter model. And we are simply using the series RL circuit. The shunt capacitance is ignored. Shunt capacitance is ignored. Why it is ignored? Because for short transmission line, we can assume that the charging current is not going to be that significant, so you can ignore it. We want to see how your short transmission line is going to look like. So, it is simply like this. It is simply like this. So this is going to be your sending end voltage. This is going to be your sending end current, receiving end current, receiving end voltage, sending end current and receiving end current. This is how we are connecting the load. Okay, this is how we are connecting the load. This is the load. Okay. Now the line impedance is here Z. That Z is that is R plus JX. That is the series resistance and inductive reactance. Yes or no? Now if you see the ABCD parameters for this short transmission line, directly you can write it is nothing but 1Z01. So if you see A is equal to D, it means this is symmetrical. And if you check AD minus BC, this is equal to 1. It means it is reciprocal also. This is reciprocal also. Now, when you talk about the performance analysis of your transmission line, whether it is short line, medium line or long transmission line, most of the time what they are asking is, they are asking the voltage regulation, one important parameter. How you are defining the voltage regulation? Please note it down. It is the change or the magnitude change in the receiving end voltage when the load is varied from no load to full load with respect to the full load receiving end voltage. Full load receiving end voltage. Very important definition. See, for a general layman, he don't know or he does not have any idea about transformers, power system or your generators or any fault or anything else. He simply checks his light or maybe other electrical equipments and he or she just check whether the voltage level is coming correctly or not. That is the only way how consumers are going to check whether the quality of power supply they are getting is good or bad. So it is very important that for any transmission line that voltage regulation should be as minimum as possible. It means from no load to full load, if the load is varied, the magnitude of the receiving end voltage should not change beyond a certain range. Okay, beyond a certain range. So in terms of equation, how we are defining it? We are defining it as voltage regulation is equal to magnitude of VR no load minus VR full load divided by VR full load. This is how we are defining the voltage regulation multiplied by 100. Now, when you talk about any transmission line, I am giving you the most general expression for finding the voltage regulation, whether it is short, medium, long, nominal T, nominal pi, equivalent T, equivalent pi, whatever type of transmission line you are having, I am going to give you one expression that will apply everywhere for voltage regulation. So you are saying, sir, Vs is equal to A, VR plus BIR. Sir, you are saying no load. No load means what? IR 0. When IR is 0, so VR no load you can write as Vs upon A. If you want to write the magnitude of VR no load, you have to write the magnitude of Vs upon magnitude of A. So if I put this value in the expression for voltage regulation, I will get voltage regulation as magnitude Vs upon magnitude A minus magnitude Vr. This Vr is full load voltage. This Vr is full load voltage upon magnitude Vr multiplied by 100. It means irrespective of the type of transmission line, if you know the value of A parameter and its magnitude, then you can define what is the voltage regulation for that particular line. Then you can define the voltage regulation for that particular line. Now let us understand something. Suppose if the A magnitude is coming as 1, A magnitude, A parameter, okay, we have discussed what is this. Suppose A parameter is coming as 1. If A parameter is coming as 1, it means what? If A parameter is coming as 1, it means the voltage regulation is simply magnitude Vs minus magnitude Vr upon magnitude Vr multiplied by 100. Yes or no? And if you see for our short transmission line, we have seen the ABCD parameters. For our short transmission line, we have seen the ABCD parameters and the A parameter is 1. If the A parameter is 1, it means for your short transmission line, you can directly use this formula. You can directly use this formula for your short transmission line. But for your short transmission line, the formula we are generally using is R per unit cos phi plus X per unit sin phi. This formula we are using when there is a lagging load. If the load is leading, then the voltage regulation formula becomes R per unit cos phi minus X per unit sin phi. This is the formula we are having when it is the leading case, when it is the leading load condition. Now you please understand, this equation you have to understand. Okay, then only you will be able to handle the further discussion and questions. Sir, what is R per unit and X per unit? R per unit we are defining as, how you are defining R per unit? R per unit you are defining as the series resistance of the line divided by Z base. What is X per unit? It is X of the line divided by the Z base. But when you are writing it, so this is for the line. This is for the line. I hope you are getting this. This is for the line. But when you are writing for the load, for load it is going to be different. When you are writing it for the load, it is something like this. Suppose this is R load, this is X load, and suppose this is the Z1. Suppose this is the Z load. So this angle actually we are defining as phi. So for the load we are defining tan phi, sin phi, cos phi as what? X load upon R load. X load upon R load. So please understand, phi is related to the load impedance. And this R per unit, X per unit is related to the line resistance and reactance. I hope you get it. So this is the general formula we are writing here. Now this formula we can use and you can make some conclusions. What are those conclusions? Let us check. First, let us see the maximum voltage regulation condition. When you are going to have the maximum voltage regulation condition. Voltage regulation means the change from no load to full load is very high. So that is only possible when you have the lagging load. Lagging load means voltage drop. Yes or no? So voltage regulation equation we are using for the lagging load. So this is R per unit cos phi plus X per unit sin phi. You have to find the maximum voltage regulation condition. Just differentiate it with respect to phi and put it to 0. So it becomes minus R per unit, cos phi becomes minus sin phi, plus X per unit, it becomes cos phi. Just put it to 0. So you get tan phi as X per unit upon R per unit. Sir, what is tan phi? We have just seen. Sir, what is tan phi? Tan phi is X load upon R load, or you can say X per unit, and this is for line, upon R per unit, and this is for line. So this is the condition when you have the maximum voltage regulation. You can also write in terms of the angle. So if yes, here, if we are writing the impedance triangle for the transmission line, and suppose this is R line or R per unit, and this is X line or X per unit, and this is Z line or Z per unit. Suppose this angle we are saying is theta. So what is theta? It is the impedance angle. It is the impedance angle of line. Sir, what is phi? Sir, what is phi? It is the impedance angle of the load. It is the impedance angle of the load. I hope you understand this difference. So if X by R line is equal to X by R load, so you can say theta is equal to phi. Hello? Or phi is equal to theta. Theta is fixed, phi is variable. So you write phi is equal to theta. Just note it down. Phi is equal to theta. Everybody just tell me in the comment section, are you getting this or not? Shall we stop? Shall we stop? So we started at 6 o'clock. I see that people are getting little tired. So if you want, we can stop also, no problem. We can continue in the next session. See, this initial part is very lengthy because this is a very lengthy subject you can understand. I am only taking the important ones. Still, it is taking too much time. So just tell me in the comment section whether we should continue or stop. Accordingly, I am going to proceed. Okay, let us complete this short transmission line, then we'll close for the day. Then we'll see in the next class. Okay. So we have seen the condition for the maximum voltage regulation. What is the value of this maximum voltage regulation? What is the value of this maximum voltage regulation? It is R per unit. Cos phi R you can write as cos theta because phi is equal to theta, plus X per unit you can write as sin theta. Sir, what is cos theta? Just see this triangle. What is cos theta? Cos theta is X per unit upon R per unit. X per unit upon R per unit. Is it okay? No, I am doing it wrong. It is cos theta. Yeah, cos theta is R per unit upon Z per unit. It is R per unit upon Z per unit. Plus X per unit. What is sin theta? Now this is going to be, sin theta is going to be X upon Z. This is going to be X per unit upon Z per unit. If we simplify this, R per unit square plus X per unit square divided by Z per unit, this is Z per unit square and this is Z per unit, so it becomes Z per unit. And this Z per unit is the per unit impedance of the line. So the maximum value of the voltage regulation is nothing but the per unit impedance of the line. Now let us see the condition for zero voltage regulation. Let us see the condition for zero voltage regulation. Condition for zero voltage regulation. Condition for zero voltage regulation. Now, zero voltage regulation is only possible for the leading load condition, because leading load condition means what? That at the receiving end, the voltage drop is going to be less. Because Vs, Vr magnitude has to be equal, then only voltage regulation can be zero. For that case, it is only possible for a leading load. Only possible for a leading load. So, which formula we are going to use? It is R per unit cos phi minus x per unit sin phi equal to 0. Directly if you do, so tan phi becomes equal to R per unit upon x per unit. R per unit upon x per unit. Sir, what is tan phi? Tan phi is x load upon R load. So this is equal to R per unit of the line upon x per unit of the line. Either you can write in this way or you can write in terms of this tan phi is actually tan phi is equal to cot theta, or you can write phi is equal to 90 minus theta. Phi is equal to 90 minus theta. Are you getting that? Are you getting that? Okay. So I think let's stop here. Let's conclude. And the next thing, next part we are going to see in the next lecture. Okay, maybe because of the change in the schedule, the students were not able to join at the right time. Okay. So friends, I hope you enjoyed the session, you learned something, and we are doing all these efforts just for you guys only, especially for 2026, and for 2027 and 2028 guys, still there is a lot of time, but for 2026 we are coming up with a lot of free initiatives so that you can join us, you can get benefited out of it. So if you like what GFG initiatives are, then you can go and join the GFG Telegram channel for EC, Electrical and IM. So you can raise your doubts, you can raise your problems. If you want help in any particular idea or spectrum, we are always there to help you. So this is all from our side. Let's meet in the next session when we are going to discuss some more important concepts for your favorite subject, power system. Till then, goodbye, take care, all the best. Thank you so much. Thank you everybody, take care. Thank you everyone, take care.